Hey, pre-calc students, this is going to be Unit 4B, Day 8, and we're getting close to the end of this unit here. We do have a pretty big day in front of us here with solving fourth-degree polynomials. So we've hopefully gotten to a place where we're pretty good at finding all the steps to solve cubic polynomials with Descartes' rule of signs, rational root theorem, synthetic division. And I'll tell you, it's not really going to change much when we solve a fourth-degree polynomial. We're still going to do those same tests, and they work the same way that they do for cubics. Okay, so we're going to do Descartes, we're going to do rational root tests, we'll do synthetic division, but there is one key big thing to pay attention to that will look a little different when solving a cubic, and I'll address that when we get there. But if you copy this down on a sheet of paper to get started with notes by hand today, we're going to jump right into it and get started with some Descartes' rule of signs and see what that tells us about the positive, negative, and complex possibilities here. So what would Descartes' rule of signs do? Well, for f of x here, we've got positive, negative, negative, positive, positive. So looking at the signs going across there, it changes once here and once here. And that 2, remember that represents the max number of positive roots that your polynomial can have. So for f of negative x, we're going to change only the signs of odd exponent terms. So x to the 4th stays, x cubed changes, x squared stays negative, x to the 1st changes. Remember that the constant will always keep its sign. So notice that this one also changes sign twice. And then what that allows me to do is come over here and make a quick little chart with positive, negative, and complex cases. And remember that since this is a 4th-degree polynomial, I need to get 4 roots in the end. So if we have a max of 2 positive and then we also have 2 negatives, well, that's already a total of 4 roots, so there would be 0 that are complex. And if you remember what's happening with Descartes' rule of signs is if you can decrease a column by 2, that would make room for a consideration of having complex roots. Complex roots come in pairs. So you could have 0, 2, 2. Maybe I'll take 2 from the positives, put them over here in the complex column. That would be another potential way the roots could turn out. Maybe the positives will stay at 2, but the negatives will decrease by 2. So 2, 0, 2 is a third way that the roots could turn out for this polynomial. And there is one last and final way. Since you can decrease each column by 2, you can do those both at once and say maybe all 4 roots are complex. And I'll tell you right now, that's definitely not going to be the case for us because then we'll never find the roots with synthetic division. If all the roots are in a plus bi form, it's going to be pretty bad news if this is what it was. So in our work in this unit, it's not going to be this case, but I still want you to write it down that it is a possibility. So we're either going to find 2 positive, 2 negatives, or maybe some other combination that we've listed in the chart here. Let's move on to rational root theorem. Remember that we're looking at the factors of the last coefficient 6, which I call P, and then the factors of the first coefficient Q, and we're going to divide those factors out and see what those possible root values would be. So the factors of 6 are plus or minus anything 1, 2, 3, and 6. Remember, you need the plus or minus there because it could be 1 times 6 or it could be -1 times -6. Factors of 4 are plus or minus 1, 2, and 4. 1 times 4, 2 times 2. So then we got to take everything on the top and divide by 1 to get our total rational root list here. Well, everything on the top divided by 1 is 1, 2, 3, 6. Now take everything on the top, divide by 2. We get 1/2. 2 over 2 is 1. That's already there. We get 3 halves and 6 halves, which is 3, so that we don't have to repeat that. But then lastly, take everything on the top, divide by 4. So you get 1/4. 2/4 is a half. That's already there. 3/4 is new. 6/4 is 3 halves. Okay, so that's our total rational root list. And it looks like just a list of 8 numbers. Technically, there's 16, though, with a plus or minus there, isn't there? So it's going to be really important with this larger list of roots, maybe than what we're typically used to be able to look for things like upper bounds, lower bounds, sign changes, all those things in synthetic division that will help us to narrow down our work faster. So here's what I'm going to do in the synthetic division step. Set up your chart where we are going to test roots on the left. The first root is always 0, just like we did for cubics. We've got to copy the coefficients carefully from the top, which are 4, -4, -25, 1, and then finally 6. Remember that last column, the remainder is the y value for the function, so that would be a remainder of 6. And to get started here, if we think about testing, let's say +1. I always start with 1 usually, or -1, depending on what Descartes' rule of signs tells me, but it's just a good kind of like get the party started root tester here, because it's typically pretty easy to test. Bring down the 4, 4 times 1 is 4, plus -4 is 0. It's okay to get zeros here, by the way. 0 times 1 is 0, plus -25 is -25. -25 times 1 is -25, plus 1, -24. Finally, -24 times 1 is -24, plus 6 is -18. So 1 is not a root. But the reason why testing 1 was kind of nice here is, check that out. We've got that sign change happening, that when we test 0, the y value is 6. When I test 1, the y value is -18, which means there has to be a root in between these. Have to cross the x-axis. So what are my options in the list? We have 1/2, 1/4, and 3/4. Those are all, I guess, potential candidates at this point. Maybe 1/2 is your go-to just because it's midway in between. We'll try it and see if it works. Still bring down the 4. Half of 4 is 2, plus -4 is -2. Half of -2 is -1, plus that -25, -26. Half of -26 is -13, plus 1 is -12. Half of -12 is, hey, -6 plus 6 is 0. So we found a root. Okay. So here's where if we were solving a cubic, we'd be now at a point where we had a quadratic left over to solve, right? Because we typically in a cubic have one less column here. So we would just have these 3 coefficients, which represent a quadratic. But since we started with something that was a 4th degree, when you find a root, what you're left with is a cubic, right? This would go with x cubed, x squared, x, and then the constant at the end. So what you have to do in this step, you can't keep using the same original coefficients in synthetic division. You have to do what's called depress the equation. Depress is not a sad thing. It means actually take it and condense it to 1 less degree. So I'm actually just going to make a whole new chart here for synthetic division, where now I'm going to test in these 4 coefficients: 4, -2, -26, and then -12. This is the only part of the process that changes a little bit. And it just involves taking these and just doing a little bit more synthetic division. Because if you now find a root within this cubic polynomial, then you'll have it reduced to a quadratic, and that's the whole goal. Okay, so maybe since we already found a positive root, by the way, it might be a good idea to switch over to negatives and just see if we can find a negative root, because it seems equally likely that maybe we'll get a positive and or negative solution here. So if I bring down the 4, 4 times -1 is -4, plus -2 is -6. -1 times -6 is 6, plus -26 is -20. And then that's going to multiply to 20, plus -12 is 8. So -1 happened to not work out, but hopefully you jumped right on that and said, wait, there's a sign change, which means there has to be a root between 0 and -1. Do you think we'll get lucky enough that it happens to be -1/2? I don't know. I mean, we could try it. If not, we have 2 other options. We have -1/4 and -3/4. So we have some other things that we can try if this doesn't work. Half of -1/2 times 4 is -2, plus -2 is -4. This would multiply to +2, plus -26 is -24. Just got to be careful with all the negatives here. -1/2 times -24 is +12, plus -12 is 0. And we did get lucky that actually -1/2 worked out really nicely for us there. So now we're at a point in the process where, since we were testing in a cubic, these represent the coefficients of a quadratic: 4x squared minus 4x minus 24. I'm going to set that to 0 to find the final 2 remaining roots, right? We have 1 root of 1/2, another root at -1/2. We have to find 2 more to get a total of 4 roots for this polynomial. Okay. So to solve this, it would make your life so much easier if you recognize that there's a GCF of 4 that you can divide out of everything. So then this reduces to x squared minus x minus 6. And the great thing about this is that it's actually factorable. If it wasn't, we have quad formula, CTS, we have strategies to solve quadratics that are not factorable, but this one happens to be nice and factorable. So finally, we get x equals 3 and x equals -2. So what I'll do in the end, and you do not have to list the roots in order, but I think it's kind of nice to do so. The roots are -2, -1/2, +1/2, and then +3. Right, so these two roots from the quadratic, and then we tested these roots in synthetic division. Those are the 4 roots of this polynomial. And guess what? If you were to come over here and go to -2 and -1/2, and maybe +1/2 and 3, based on what we just did, you can get a really accurate little W sketch here for this 4th degree polynomial, just based on those roots, okay? So based on those 4 locations here, we know that both tails are going to go up because the lead coefficient was positive. We know a lot of things at this point. That's what the process looks like, okay? So I might go a little bit faster through the next example, but I think we benefit from doing one more. Of course, as I write this next one down, if you're like, you know what, I'm ready to like fly on my own and try this one. Of course, you can hit pause and see if you get the same results in the end, but all we're going to do is just one more example. Finding all the roots of this 4th degree polynomial. Okay. So for our last example in the notes, we'll do 6x to the 4th minus 5x cubed minus 23x squared minus x plus 3 equals 0. Okay. Might go a little faster, so of course you can slow it down if you need to. For Descartes' rule of signs, the signs go plus, minus, 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 plus. And I see, oops, that was supposed to be this right here. 2 sign changes in f of x. F of -x, change the odd powered terms. So x to the 4th stays, change it, keep it, change it, keep it. All right, so we've got 2 sign changes going on there as well. So your positive-negative complex chart, I'm not going to spend a lot of time talking about it because it's the same one that we just did in number 1. The first case was 2, 2, 0. The other possible cases, if you reduce by 2 at a time, or maybe doing both columns by 2. Those are the other ways that the roots could turn out. Hopefully you've done Descartes up until this point enough times for you to feel pretty confident with how that all works, but if not, you'll let me know. All right, let's go on to the rational root theorem so we know what roots we should be testing with synthetic division. Remember, P is the last coefficient, so factors of 3 are plus or minus 1 and 3. Q is the first coefficient, factors of 6, plus or minus 1, 2, 3, 6. It's not necessarily common to have more factors in the bottom than on the top, but that's okay. Okay, but it's probably going to produce a lot more fractions. So if I take these numbers and divide by 1, we get 1 and 3. Now take those numbers, divide by 2, you get 1/2 and 3/2. Now take them, divide by 3, we get 1/3. 3 over 3 is 1, already in the list. And then take them, divide by 6, you get 1/6, and 3 over 6, which is 1/2, but that's already in the list. So there's your list of possible rational roots. Looks like a list of 6, but technically, with the plus or minus there, we've got 12 roots we could be testing. All right, synthetic division, set up a chart. All right, 0 goes here. The coefficients are 6, -5, -23, -1, and then separate in the last column there this 3. Okay. So if we go ahead and start testing something like 1, bring down the 6. 6 times 1 is 6, plus -5 is 1, times 1 is 1, plus -23 is -22, times 1 is -22, plus -1 is -23. Going kind of quickly here, but synthetic division, we got to get good at it. -23 times 1 is -23, plus 3 is -20, and not a root, but sign change. Okay, so our go-to has been 1/2. Let's try it. Bring down the 6. 1/2 of 6 is 2, plus -5 is, oops, 1/2 of 6 is 3. That was a bad mistake. 3 plus -5 is -2. Okay. 1/2 of -2 is -1, plus -23 is -24. 1/2 of -24 is -12, plus -1 is -13. Uh-oh. So half of negative 13 is negative 6.5, right? Plus 3 is going to be negative 3.5 in this case. So 1/2 definitely doesn't work. Oh man, 1/2 has always been our go-to. Well, we have other options between 0 and 1. We have a third and we have a sixth. We can try one of those. Let's try a third. So bring down the 6. 1/3 of 6. Just think about dividing it by 3, right? So that would be 2. 2 plus negative 5 is negative 3. If I think of dividing this by 3, that's now negative 1. Plus negative 23 is negative 24. Divide by 3, negative 8 plus negative 1 is negative 9. Divide by 3, negative 3 plus 3 is 0. So we find that 1/3 is in fact a root. Excellent. All right, so now we can move on and do that critical step where we depress the equation. And if you don't do that, you're going to get stuck. You're never going to get down to a quadratic. So it is a really important step. So take these coefficients that represent a cubic polynomial, 6, negative 3, negative 24, and negative 9. One quick note is that sometimes I don't make a whole new chart. Sometimes I kind of just like ignore this column and I use this as my new testing ground. But I think, to be honest, if you just make a new chart, it's going to make your life that much easier. All right, so what do? We kind of switch over and we start thinking about maybe testing some negatives. So when I bring down the 6, I'll test maybe negative 1. Negative 1 times 6 is negative 6 plus negative 3 is negative 9. That would be 9 plus negative 24 is negative 15. And then 15 and negative 9 is 6. You don't always get a sign change here, guys, but if it happens to work out that way, you know, maybe it's not a bad thing to look for. Okay. But here's what I'll tell you. If you wind up testing negative 1/2 and something like negative 1/3, just to save us a little bit of time in the video, I'm going to tell you the remainders for both of those are not 0. You get 3/2, you get negative 14/9. Okay. So neither of those work. And it's like, wait, but a negative 1/6 won't work either, by the way. So nothing in between those roots work, but it says there's a sign change. Don't we cross the x-axis? And the answer is yes, but we're going to have to talk about that when we get our end answers. I'm going to be a little crafty and be a good guesser of negative 3/2. So if I test negative 3/2, we bring down the 6. How would I test negative 3/2? 2 goes into 6 3 times. 3 times negative 3 is negative 9. Plus negative 3 is negative 12. Divide the 2 in first, so that's negative 6 times negative 3 is 18. 18 plus negative 24 is negative 6. Divide the 2 in, negative 3 times negative 3 is 9, plus negative 9 is 0. So it does turn out that negative 3/2 is a root. Maybe not our favorite one from the list of possibilities, but it's in there. It was possible to test. So what do we get left over? 6x squared minus 12x minus 6. And just like we had in the last example, it's not always like this, but you can divide out a big GCF of 6 there to get x squared minus 2x minus 1. And this looks factorable because we're like, oh yeah, multiplies to 1 and adds to negative 2, but it's not. Multiplies to negative 1 and adds to negative 2 is not a possible factoring trinomial here. So I'm going to solve this by CTS. I'm going to complete the square. If you want to use quadratic formula, we should get the same answers. But I'm going to add this 1 to the other side. And then to complete the square, b over 2 squared is going to be 1. So you're going to add 1 to both sides. You should be pretty good at solving quadratics with whatever algebraic technique you're most comfortable with. So square root, x minus 1 equals plus or minus the square root of 2. So we get 1 plus or minus the square root of 2 as the other roots. And just out of curiosity, let's take a look at what those are as decimals. So 1 minus the square root of 2 is about negative 0.4, and 1 plus the square root of 2 is 2.4. So if I think about the total list of roots that we have negative 3/2. And again, you don't necessarily have to list them in order, but technically if they were in order, the next one would be 1 minus radical 2, because it's negative 0.4. And then from there, we would have 1/3, and then 1 plus the square root of 2. These roots, by the way, are not complex. This is a negative number, and this is a positive number. So we do get 2 negatives and 2 positives, just like Descartes says was a possibility. and it is going to wind up crossing the x-axis. There's a super of sketch, but in 4 places, 2 negative locations and 2 positive locations. But one thing I want to address is come back up here and say, wait, why did that sign change happen? Did we actually cross the x-axis between 0 and -1, actually? Sorry, that's what we're looking at. That was where that sign change happened, but none of those roots were. Yeah, it crossed that positive 1, minus radical 2, which is about -0.4. So when you get this sign change in your synthetic division, it doesn't guarantee that it's crossing at an irrational location, meaning a fraction or an integer or something in my list. It is guaranteed to cross the x-axis, but in here I didn't know where it was going to cross until I got to this quadratic stage, because it happened to cross at an irrational location, 1 minus radical 2. And that's a little bit of a tough concept, but all I'll say is don't do this sign change business and think that you made a mistake if none of these roots test. Maybe it's not actually crossing at a rational location. A lot of times it is, by the way. Maybe it's actually crossing at an irrational location like this one was. And that's one of these nuances of this whole process that, just with some practice, you'll start getting used to. But hopefully you understand what this process is all about, finding all of the roots. And we've got a lot more practice coming your way with finding roots of 4th degree polynomials. Have a great rest of your day.